right, so here is our second example in which we are going to solve this initial value problem. Now, it's in this problem that what I started off with, talking about how we were actually looking at some exponential growth situations, is going to come into play somewhat here. So again, the first thing I'm going to try to do is separate this so I can go ahead and solve. So as I go ahead and I do that, then we can take the integral of each side to find the antiderivative. And so we still end up with our natural log of the absolute value of y equals, now when I'm taking the antiderivative here, I know it's negative 2x squared over 2 plus c. So right now I'm sitting with an equation that's the natural log of y equals negative x squared plus c. Now, again, what we're going to end up doing is trying to solve for y. So in order for me to do that, what I'm going to do right now is I'm going to rewrite this in exponential form. So I know natural log of the absolute value of y, that means it's base e. So when I go ahead and I canoe that, for those of you that know what that is, I end up with e to the negative x squared plus c equals the absolute value of y. Now, from here, I'm going to do a few different things. Now, what I'm going to do is I'm going to give the plus or minus to the e, so I have y equals plus or minus, and then I'm going to rewrite this. So now remember, if we're adding exponents, that means at some point we had to have been multiplying with the same base. So I can rewrite e to the negative x squared plus c as e to the c, and that looks like a 0. I don't want to confuse anybody. E to the c times e to the negative x squared. Now, here is where this is going to differ a little for you all. Now, when I'm at this point, I'm looking at this plus or minus e to the c. Well, I know plus or minus e to the c, that's representing some constant. And so in this case, I'm going to call this constant k. And from everything I've been looking at, it seems to be a pretty consistent variable that gets used. Now, if I go ahead and I rewrite this as y equals k e to the negative x squared. Well, what I'm going to do now, though, is I'm going to use the fact that I have this initial condition of y of 1 equals 4, because I still have to find k. So we end up with 4 equals k times e to the negative, and then my x is 1, 1 squared is 1, so to the negative 1. So hopefully you guys know that e to the negative 1 could be rewritten as 4 equals k over e. And so if I'm trying to solve for k, now I can just go ahead and multiply both sides by e. And I'm left with the fact now that k equals 4e. So now I have k, and so I'm just going to take this k equals 4e, and I'm going to plug it right back in there. So my final answer is going to be y equals 4e times e to the negative x squared. And I can rewrite this if I want as 4e to the 1 minus x squared. Either one is okay. But that is the solution to this differential equation with this initial condition. And our last example. So again, we're going to do something similar to what we've just done. So this time around, what's interesting is I've got my x and my y inside of that variable, or inside of that exponent. So I got to figure out what I can do to separate that. But again, if I have the addition, this is essentially addition, I can rewrite this so that it's e to the x times e to the negative y. Because remember, if I was going to simplify this and they have the same base, I would add my exponents, which would put me right back there. So now I have dy dx equals e to the x times e to the negative y. So what I'm going to do now, though, is I'm just going to go ahead and rewrite all this. And so I'm going to start manipulating things and moving it around. So I know I could multiply both sides by dx, so I'd end up with e to the x dx here. And if this is e to the negative y, well, we know that that could have been over e to the positive y, which then means I could just multiply it to the other side. So I have e to the y dy. So now that we have our variables separated, and we go ahead and we find the antiderivative, well, we know the antiderivative of e to the y dy would just be e to the y equals e to the x, but now I have this plus c here. So it's at this point that there's going to be kind of two different things that we need to do from there. One of them is going to be that we need to go ahead and we need to solve for y. The other is going to be is that we need to find c. And so we kind of do these parallel to one another in a way. So what I'm going to do when I go to solve for y is I need to get it out of that exponent. So what we can do is we can just go ahead and take the natural log of both sides. Well, the natural log of e to the y is going to be just y. For those of you that don't remember that property, the other way to think about it is if you took the y and moved it to the front, then we have y times the natural log of e. The natural log of e is 1. So now we're left with y equals the natural log of e to the x plus c. And so this is now going to be where I start to solve for c. But when I start to solve for c, I'm starting with this equation when we left off that one. Because I can technically plug it in any time I want. I just want to do it the easiest way possible. So if y is 2 and x is 0, we end up with e to the second equals e to the 0 plus c. So e to the second equals 1 plus c. So now I have e to the second minus 1 equals c. So instead of taking it and trying to plug it back in there, I'm just going to take this e to the second minus 1 and plug it back in there. So my final answer ends up being y equals the natural log of e to the x plus e to the second minus 1. And so this is the particular solution to that differential equation. So I'm going to post some homework assignment for you guys to work on, a few problems to look at. Go ahead, do the homework, check your answers, and let me know if you guys have any questions. And we will go from there, and hopefully I'll see you Wednesday. If not, I'll see you back here on this Lego tower that I've built to put my iPad. And that is all for now, folks.